Hi dear students, this particular class I am going to discuss about inclusion and exclusion principle at the same time, that is using that dearrangement principle also we are going to discuss. What is an inclusion and exclusion principle? Observe here, you know about A union B. At the same time, number of elements in A union B also you know. This is a universal set. Here one set is say A, this is another set B. Let us say this is equals to A and this is equals to B. So this portion represents A only and this portion represents B only, right? And this one represents the common portion A intersection B. Suppose you want to find out the number of elements in A union B. Number of elements in A union B means what we will write? Number of elements in A, we are including number of elements in A plus number of elements in B. That means in that case this particular portion also coming. So what happens? Number of elements in A, intersection part is coming. Number of elements in B, again intersection part is coming. That means A intersection B is appearing two times. That's why one time we are excluding. So minus n of A intersection B. In a similar way, suppose we have n of A union B union C is there. So observe here, this is the n of A union B union C. This is the circle A and this one represents B and this one is C. A, B, C. You know this entire rectangle represents universal set. So this one represents the number of elements in A, number of elements in B, number of elements in C, number of elements in A. Observe this particular portion. Number of elements in B, this particular portion appearing two times, but this portion is appearing in both the cases. So that's why we are removing number of elements in A intersection B minus number of elements in B intersection C minus the number of elements in A intersection C. We are excluding that part, and again when we are excluding that, because this particular part number of elements in A will come, number of elements in B will come, number of elements in C also this particular portion will come, but number of elements in A intersection B we are removing, this part is removing. N number of elements in A intersection C, this part is removing. Number of elements in A intersection C, this part is removing, right? So that's why we have to add this particular part. So excluded, again we are including, that is the number of elements in A intersection B intersection C. Observe here, sigma of number of elements in A, that means A, B, C will come, minus number of elements in A intersection B. So what is the meaning here? A intersection B, B intersection C, C intersection A, plus number of elements in A intersection B intersection C. Suppose we want to extend this one for n sets. The same idea we are extending for n sets. Then what happens? This inclusion and exclusion principle. This is the observation. Number of elements in A1 union, A2 union, right? Number of elements in A1 union, A2 union, A3 union and so on union AN. Number of elements in A1 union, A2 union, A3 union and so on AN is nothing but summation number of elements in ai. So what is the meaning for that? Summation n of ai means a1 number of elements in a1 plus number of elements in a2 plus number of elements in a3 plus and so on plus number of elements in an. That means these single sets, how many you will get? From n different sets we have to select one at a time. That means nc1 terms you will get in this summation. In this summation you will get nc1. Next we have to exclude summation number of elements in ai intersection aj excluded. Here how many sets you will get? These type of sets you will get, how will get? From n at a time we have to select 2. That means in this summation total nc2 elements are there, nc2 terms are there. Next again include summation number of elements in ai intersection aj intersection ak. But here how many elements you will get? This summation consists of how many terms? We are taking 3 at a time. Number of elements in this summation is nc3. From n we are selecting 3 at a time. So finally plus and so on plus minus 1 whole to the power of n minus 1 into, you see in case of 3 a b c case it last term ends with plus or not. So 3 minus 1 minus 1 whole square, it becomes plus. That's why minus 1 whole to the power of n minus 1 into number of elements in a1 intersection, a2 intersection, a3 intersection and so on intersection an. If n is even, the last term ends with minus. If n is odd, the last term ends with plus. So that is about inclusion, exclusion. Inclusion, exclusion. Now observe here, how many terms are present here? Single terms, a1, a2. From n elements we have to select 1 at a time. Whereas here from n we have to select 2 at a time. Total how many terms are there in this summation? nc2. In this summation how many terms are there? nc3. This is the only one term ncn, right? So now my question is this one. There is a word Dispor. Dispor is the capital of Assam. Now he is asking number of different words that can be formed by using all the letters of the word Dispor, so that neither di nor sp, neither di nor sp appear. Neither di nor sp appears. Here I am taking a denotes di appears. Next b denotes sp appears. So what about a intersection b denotes? Both appears. Di appears means what happens here? S P U R. So 1, because we are considering this one as one unit, di has to appear always. Okay, so di we are considering as one unit. 1, 2, 3, 4, 5 units. They can be arranged in 5 factorial ways. Next what is saying? SP has to appear. So that's why forward take SP as a single unit, remaining D, I, U, R. So they can be arranged in 5 factorial ways. Next I am finding DI appears, SP also appears. Now what are the remaining? DI appears, SP also appears, remaining we have UR. So this one we are considering as one unit, this one we are considering as another unit. 1, 2, 3, 4. They can be arranged in 4 factorial ways. Now what is the meaning for n of A union B, meaning number of elements in A plus number of elements in B minus number of elements in A intersection B. Its meaning is at least one of Di or Sp appears. At least one, that means Di may appear, Sp may appear, or both may appear. I am finding at least one of these two appear. But what is asking in the question? None of them appears. Neither Di nor Sp appear. Neither Di nor Sp has to appear. Total with the letters of the word dispore. With the letters of the word dispore, how many different words can be formed? 6 factorial different words are possible. These are the total words that are possible with the letters of the word dispore. But what is saying in the question? Neither Di nor Sp has to appear. So this is the answer for either Di or Sp appears. That means at least one of these two appears. At least one means what? Either one or two. At least one means either one or both appears. Okay, so that's why from the total number of possibilities, if you are subtracting this one, at least one appears, then we will get neither nor appears. So this is the answer for the number of different ways to arrange all the letters of the word dispore so that neither Di nor Sp appears. Okay, from total number of possibilities I am subtracting at least one of Di or Sp appears. At least one of Di Sp appears I am subtracting. Okay, so this is the basic funda for deriving the dearrangement principle also. First of all, what is the meaning of dearrangement? The name itself is saying that dearrange. Dearrange, that means no letter is in its original position. No letter is in its original position. Suppose you see S, I, T, sit. So now I, T, yes. No letter is there in its original position. This is the original word. We manipulated these words in such a way, no letter is in its original position. This is S original position, I original position, T original position. Now you can see, observe this arrangement. No letter is there in its original position. Now you can observe, this is T. Here I am filling S. Here I am filling I. Here also the same. No letter is there in its original position. This is the original position of S. This is the original position of I. This is the original position of T. No letter is there in its original position means these are the possibilities. That is dearrangement. Okay. So dearrangement means no letter, no object is in its original position. Okay. So how to find out the number of dearrangements? Suppose we have n distinct objects are there. These n distinct objects, let us say here A, B, C, D and so on, like that. Total we have n different objects are there. These n different objects we have to fill in n numbered boxes. Okay, so all these n different objects not there in original position, dearrangement. Okay, so for that what I am doing is, so total these n letters can be arranged in how many ways? N factorial ways can be arranged. N factorial ways we can arrange. Now what I am doing here is, I am considering A1. So what is the main funda behind this particular problem is total number of arrangements minus Total number of arrangements minus at least one letter. At least one letter is in its original position. At least one letter is in its original position means what we have to find out? We have to find out this one. A1 union, A2 union, A3 union and so on, AN. Number of elements in A1 union, A2 union, A3 union and so on, AN we have to find out. Sir, what is A1? A1 denotes exactly one letter is there in its original position. A1 denotes exactly one letter in its original position. A2 denotes exactly two letters are in its original position. A3 denotes exactly three letters are in their original positions. Right? So what is A1? Exactly one letter in its original position. A2 denotes exactly two letters are in its original position. A3 denotes exactly three letters are in their original position. Now, total number of possibilities minus, we have to find out this value, because at least one letter is in its original position means we have to subtract this value. This is nothing but this total summation. So what is this first one meaning? N of AI. Okay, ith letter is in its original position. Okay, suppose you see this is the letter. This letter must be in its original position only. This letter is in its original position means you forgot about this letter. Remaining how many letters are there? N minus 1 letters are there. Those n minus 1 letters can be arranged in those n minus 1 places in how many ways? N minus 1 factorial ways. Okay, first of all, this summation consists of how many terms? NC1 terms. That's why NC1 into, that means I selected A. Why A? You can select B also in its original position. C also in its original position. That's why NC1. Okay, suppose I selected A is there in its original position. Exactly one letter is there in its original position. Now A is there in its original position. Remaining n minus 1 letters can be arranged in n minus 1 factorial ways. Minus. Now what to do here? A1 intersection AI intersection AJ. Total how many elements are there in this summation? NC2 elements are there. NC2 elements are there. Okay. So A1 intersection A2. A1 intersection A2. It means exactly two letters are in its original position. Exactly two letters are in their original position means observe this one. Observe this one. Now these two letters are in their original position. Remaining how many letters are there? N minus 2 letters. Those n minus 2 letters can be arranged in how many ways? N minus 2 factorial ways. Next plus NC3 into, that means out of n we are selecting 3 letters, right? So now those 3 letters are there in their original position means remaining n minus 3 letters can be arranged in n minus 3 factorial ways, plus and so on. If you continue, plus minus 1 whole to the power of n into, actually minus, plus minus and so on, NC n into 0 factorial. Every letter is in their original position only, that is only one way. This is the answer we got. Now you can see this simplification, n factorial minus NC1 can be written as n factorial divided by n minus 1 factorial into n minus 1 factorial minus nc2 can be written as n factorial divided by n minus 2 factorial into n minus 2 factorial plus nc3 means n factorial by n minus 3 factorial into n minus 3 factorial plus and so on plus minus 1 whole to the power of n. N means what we can write? N factorial divided by 0 factorial into n factorial. Okay, so now n minus 1 factorial, n minus 1 factorial, n minus 2 factorial, n minus 2 factorial, n minus 3 factorial and cancel. If you are taking n factorial common, right? From all the equations, if you take n factorial common, then what we will get? Here 1 minus 1 by 1 factorial, because we are taking minus inside, plus 1 by 2 factorial minus 1 by 3 factorial plus and so on plus minus 1 actually whole to the power of n minus 1 here. When we are taking this minus inside, you will get minus 1 whole to the power of n into 1 by n factorial. So out of n letters, all n letters are dearranged. That means it is the meaning of dearrangement of n objects. Total n objects are there, means all those n objects we have to dearrange. That is given by n factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus and so on plus minus 1 whole to the power of n by n factorial. So here minus 1 whole to the power of n minus 1. That's why here also minus 1 whole to the power of n minus 1. Here also minus 1 whole to the power of n minus 1. Because when we are multiplying minus inside, here minus 1 whole to the power of n you will get. Okay. So that is about the dearrangement principle. So Dn, observe here the question is saying like this. Total 4 letters are there. 4 letters and 4 addressed envelopes are there. 4 letters and 4 addressed envelopes are there. These 4 letters are randomly arranged in those 4 envelopes, one in each. These 4 letters can be arranged in those 4 addressed envelopes. Okay, this every letter has their own address. So these 4 letters are arranged in these 4 addressed envelopes randomly. The question is asking number of ways that all the letters will go to the wrong address. All the letters will go to the wrong address. That means, suppose you see here, this is a letter 1 and this is a letter 2, this is a letter 3, this is a letter 4, letter 1, letter 2, letter 3, letter 4, and this is envelope 1, and here envelope 2, this is envelope 3, and this is envelope 4. What is saying in the question? All the letters has to go to the wrong address. So that means all the letters are dearranged. So that is nothing but 4p, 4 into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial. So that is the answer for the number of dearrangement. All 4 letters will go to the wrong address. That can be written as 4 factorial divided by 2 factorial minus 4 factorial divided by 3 factorial plus 4 factorial divided by 4 factorial. Now you can simplify further here, right? 4 factorial by 2 factorial means you will get 12 minus 4 plus 1, that is equals to 13 minus 4. Total we are getting 9 possibilities. Now in the same question he is asking out of 4 letters exactly 2 letters will go to the wrong address. So out of 4, 2 letters has to go to the wrong address. 4p2 into 1 minus 1 by 1 factorial plus 1 by 2 factorial. That's all. That is the answer. So you know 4p2 value 4 into 3 divided by 2, that is equals to 6 ways is the answer. Okay. So this is the another question here. Question is asking like this. The letters of the word sword, S-W-O-R-D. So no letter is there in its original position. No letter is there in its original position. So that's why we have to find out the dearrangement. Total how many letters are there? 5 letters are there. That we can write it as 5p5 into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial minus 1 by 5 factorial. So that no letter is there in its original position. The number of dearrangements of 5 objects. These 5 different letters not there in their original position. So this is the answer for that particular question. So this is another question given here. Total we have 6 letters. This is the previous year's question. Letter 1 and letter 2, letter 3, letter 4, letter 5, letter 6. Total 6 letters are there and we have 6 envelopes are there. E1, E2, E3, E4, E5. Not exactly the same question, almost the same idea. Total we have 6 letters are there and 6 envelopes are there. These letters can be arranged in these envelopes in total 6 factorial ways. He is asking in such a way the number of ways so that no letter is there in its original position. No letter is there in its original envelope because this letter envelope is this one. This letter envelope is this one. That means no letter is there in its original envelope means this letter is not going to this envelope. Somewhere it is matching. Okay. So he is asking in the question, no letter is there in its original envelope, but L1 is always in E2. L1 has to enter always into the envelope 2. So this has to go here. But suppose I am assuming L1 is entering into E2, remaining all letters are dearranged. How many ways? The number of ways I don't know. Let us say I am assuming X ways. When L1 is dearranged, the remaining letters also dearranged in X ways I am assuming. Okay. But L1 is entering into E2, X possibilities means similarly when L1 is entering into E3 also X possibilities. When L1 is entering into E4 also same X possibilities. When L1 is entering into E5 also same X possibilities. When L1 is entering into E6 also X possibilities. Once again, when L1 is entering into E2, how many dearrangements are possible we don't know. I am assuming when L1 is entering into E2, remaining 5 letters can be arranged in these 5 envelopes. That is D5. Dearrangement of 5 objects because this is already matched. Now the remaining 5 letters dearranged in these 5 envelopes in how many ways? That is D5. Dearrangement of 5 objects. So when L1 is entering into E2, the number of dearrangements is X. Similarly, L1 entering E3 also same X. That's why total X plus X plus X plus X, you will get 5 times X. Okay. So 5 times X is nothing but D6. Okay. So that's the reason here, because L1 is entering into E2 case answer, L1 entering into E3 case answer, L1 entering into E4 cases, all these nothing but these 6 letters can be rearranged in these 6 envelopes in how many ways? Okay, so that's why this is completely, you will get D6, therefore you will get X is equals to D6 divided by 5, right? So that is the answer. X value D6 is what? Therefore X is equals to 1 by 5 into D6 is nothing but 6 factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial plus minus 1 by 3 factorial plus 1 by 4 factorial minus 1 by 5 factorial plus 1 by 6 factorial. Okay, so this is the answer for that particular question of arranging these 6 letters can be rearranged in how many ways. So what we did, so DL1 is entering into E2, number of ways I am assuming as X. So L1 entering into E3 case also same X possibilities, E4 case also same X possibilities, E5 case also same X possibilities, E6 case also same X possibility. That's why 5 times X is equals to dearrangement of these 6. That is nothing but D6. D6 is nothing but this one, 6 factorial into 1 minus 1 by 1 factorial plus and so on plus 1 by 6 factorial. So divide with 5, you will get the value of X. What is X? Number of dearrangement of these 6 letters in the 6 envelopes, so that L1 is always in E2. So that is the few applications regarding dearrangement of the objects. Okay, so bye bye.